In this example, we are tasked to graph the set of parametric equations by making a table of values. The graph that we will be creating is called the Witch of Agnesi, which comes from a mistranslation of an Italian word and from the Italian mathematician Maria Agnesi. We have the functions x equals 2 times tangent of t, and we have y is equal to 5 times cosine squared of t. We are told that t is restricted to be between negative pi halves and pi halves, not including those two values. And we are recommended to use increments of pi over 6. So we will do that. Due to the nature of some of the rounding that we will have in this problem, I'm going to keep the calculator up for quite a while here. But based on that recommendation, I will start by plugging in negative pi over 3, negative pi over 6, 0, pi over 6, and pi over 3. Those would be increments of pi over 6. We have negative 2 pi over 6, negative 1 pi over 6, 0 pi over 6, etc. We also need to keep in mind that t is between negative pi halves and pi halves, which doesn't include those values, but does include everything up to those values. So whatever trend we see going off on either direction here, we're going to keep in mind in order to complete this curve. But let's plug in these initial values, starting with negative pi over 3, and we'll get x and y in response. If I plug in negative pi over 3 in for tangent, we should know that one that's in quadrant 4, so it's going to end up being negative. And because it's sine over cosine, that should be square root of 3. So that should be negative square root of 3 times 2, which gives us negative 3.46. For cosine, though, that'll be 5. What this means with the square is that we are taking 5 cosine of t, and cosine of t is being taken to the second power. So if I use parentheses appropriately for that, that'll be cosine of negative pi over 3. And that is being squared, which is really just 1/2 squared, or 1/4. So this is 5/4, or 1.25. Also, do not be thrown off by the fact that y is working with cosine here. When you define functions, you can really do anything with parametric, and all that really changes is the direction of orientation when you change functions. If I do the same thing with negative pi over 6, we'll have 2 tangent of negative pi over 6. That should be the square root of 3 over 3 times 2. That gives us negative 1.15. That's our x value, and then our y value, that'd be 5 cosine of negative pi over 6. Taken to the second power, which isn't too bad. That would be square root of 3 over 2 squared, or 3/4 times 5. So that's 15/4. So that's 3.75. For 0, we shouldn't need a calculator for that. Tangent of 0 is just 0, so 2 times 0 is 0. Whereas cosine of 0 is 1. 1 squared is still 1, and then multiply that by 5, and you'll get 5. Now, when I do the same values of pi over 6 and pi over 3, I'm going to get the same absolute numbers that I did for x and y. However, the x values are going to become positive because I'm plugging in quadrant 1 angle measures now for tangent. So I will get 1.15 here and 3.46, both of those being positive. And then I'll also have 3.75 and 1.25. These are still going to be positive because cosine is still positive in quadrant 1, and more importantly, I'm squaring the result of cosine anyway. So it's always going to come out to be positive. So these are going to be helpful values, and we can also recognize what's happening to the general trend. it seems that as my t gets smaller, so closer to negative pi halves, x is getting progressively more negative, y is getting smaller and smaller, and this, in this case, is going to get closer to 0. Whereas as I get closer to pi over 2, x is getting larger and larger, but y is yet again getting closer and closer to 0. If you would like to test a value, for example, pi over 2 minus 0.1, that would be something that's close to pi over 2, but not quite. I can try that. 2 tangent of pi over 2 minus 0.1 was just a little bit off. I get 19.93. So pi over 2 minus 0.1. I get 19.93. So yeah, x does seem to be getting progressively larger. And then I can do that for cosine as well. 5 times cosine of pi over 2 minus 0.1. That is squared. That gives me a very small value, 0.05-ish. And that again follows through the trend that I was seeing. X is getting a lot larger, but y is getting just closer to 0. Let's see if we can graph that and represent it. Starting with my earliest point on the t table here, we have negative 3.46 and 1.25. That puts us around here. Then we have negative 1.15 and 3.75. Puts us about here. I'll say 1 and 2, but there's going to be a caveat to that. Third point I have is 0 and 5. That puts us on the y-axis up here. It's our third point that we have in our table. Fourth point we have on the table is 1.15 and 3.75, which is the same as the second point, or at least the same height. Just the other side of the y-axis. And then the fifth point we have here is 3.46 and 1.25. Just like the first point we plotted, but on the other side of the y-axis. About there. Now, from the trend that I was noticing, it seemed that as I got closer to negative pi over 2 or pi over 2, x was approaching an infinite value. It was either approaching negative infinity or approaching positive infinity, whereas y in both cases was getting closer to 0. That means I can think of y equals 0, or the x-axis, like an asymptote. I'm getting closer to this y-axis, or this y equals 0, and I'm not ever going to touch it. X is going to get progressively closer to negative infinity or positive infinity. Meaning that what I have is not just this curve, but also these tails. The last point, the 19.93, 0.05, would be graphed far off in the distance to the right. And there should be an equivalent negative 19.93 and 0.05 far to the left. So you can get an expectation of what this would look like. With the orientation, though, we started from the left over to the right, so we should have orientation arrows mapping in that direction. This is the curve known as the Witcheveg-Nesi, which sometimes has more common names, and when scaled appropriately, can also be connected to the normal distribution, or the bell curve.